Now, relative to my rigorous or formal definition of limit, let's just imagine I'm dealing with the graph equation y equals f of x. It's pretty darn clear that the limit of f of x as x approaches 4 is indeed equal to 2. No tricks, the curves nicely behave in the right-hand plane. However, going back to my formal definition, if epsilon is this, how must we choose delta? So, gosh, you know, when I gave that definition, I should have given some other verbal description. How about this? Before we get started with this, imagine it's my job to work in a factory where I'm manufacturing ball bearings. And I'm at the machine getting ready for the day, and my boss pokes her head in the door and screams at me. Today, you're going to manufacture ball bearings of volume 1 cubic millimeter. And if you deviate by 10%, that is to say, if you deviate by 1/10 of a cubic millimeter, you're fired. And so I've got my epsilon tolerance value of 1/10 of a cubic millimeter. I've got my L value of 1 cubic millimeter. But I'm starting to panic because when I look at my machine, it's calibrated in terms of the radius of the sphere, not the volume. Now I get that the radius needs to be the cube root of 3 over 4 times pi, but I'm worried about how far I can deviate from that A value, that radius value, to guarantee me that I'm no more than 1/10 of a cubic millimeter off of 1 cubic millimeter. And so how far I can deviate with my radius value of the cube root of 3 over 4 times pi is going to be my delta value. So if that kind of made sense, let's do the same thing over here. So someone's telling me that I want a y value 2, and I want to deviate from 2 by no more than 1/10 of a unit. And I'm being asked to find the corresponding delta value relative to my formal definition of the limit. Now, everybody, please always excuse me with scale. I don't really care what the scale is. I just need to deviate from 2 by physically a lot so you can see it. I know I'm exaggerating. So allow me. Let's see how I'm going to choose my x values so that I'm guaranteed y values that are within 1/10 of a unit of 2. So maybe with my red pen, or my blue pen, excuse me. At these 2 points, let's come down to the x-axis, albeit I am quite exaggerating. And if you guys don't mind, sorry, I need to cheat. 2.1 squared is 4.41. 1.9 squared is 3.61. So no tricks. Let's talk about a yes or no answer. Is it true that if I choose x between this blue number and this blue number, that I'm guaranteed y values within these 2 black numbers? And the answer is, heck yes. But that doesn't really get to what the delta is, because delta needs to be a number. It needs to represent how far I deviate from 4, either left or right, so I'm guaranteed a corresponding y value within epsilon units of L. And so what I'm going to do to find my delta value is I'm going to choose delta to be one of these 2 values, either the deviation between 4 and the smaller one, or the deviation between the larger one and 4. This, of course, will give me deviations of, I don't know, is that this? So if I choose delta to be the large one, then if I deviate from 4, no more than that many units to the right, everything is fine. I'm guaranteed a y value within epsilon units of L. But if I choose delta to be this large one, and I move to the left of 4 that many units, I'm outside this horizontal band that you see in blue, and I'm not guaranteed a y value that's within epsilon units of L. In the way I drew my picture with my particular function, I'm not. I could be, but I'm not guaranteed it. And so how I'm going to choose delta is in the following fashion. I would choose delta to be the minimum of these 2 deviations. And in this particular example, that happens to be this. I don't know, everyone. I don't know if I really like my question. I was just panicking and trying to find some kind of illustration that kind of illustrates the actual definition. I think what's more important is for me to sit down and start proving mathematical statements. That is what I care very much about, and that is what's coming next.